we're gonna talk about chemistry. Chemistry, sometimes it can be hard to understand it or to find the methodology to apply to real life. So today, I'm Dr. Silvera, and with other doctors, we're gonna explain to you polarity. Through this video, you're gonna hear a lot of maybe names that you have heard before, such as electronegativity, molecular shapes, polarity, solubility, and more. Polarity is a physical property that is correlated to boiling, melting point, solubility, and intermolecular relationships. Polarity, as the definition is the uneven partial distribution of charges. It can be classified as a polar and nonpolar covalent bonds. When it comes to solubility, polarity is like to like. When you have a polar molecule, it dissolves with a polar solvent, and when you have a nonpolar molecule, it dissolves with a nonpolar solvent. Solubility plays an important role when it comes to polarity. Solubility is the maximum amount when a solvent can dissolve a solute in a chemical reaction. As solute and solvent attraction, it plays an important role when discovering the solubility. When we have a solvent high attraction, we have a high solubility. When we have a solute and solvent low attraction, we have a low solubility.
The solubility rule table is going to help us understand some exceptions to find out if a compound state is aqueous or solid.
Hi, I'm Dr. Cruz and I will explain electronegativity. Electronegativity is the ability of an atom to attract electrons from another atom. There are two cases, one that is formed by two non-metals and one by one metal and no metal. In the first one, it's called molecular bonds, and as you can see, this means that the chlorine, that is the most electronegative one, will attract electrons from the hydrogen. It doesn't have enough force to pull out all the electrons, but that's why they share them, becoming they're more stable. The second one is called ionic bond. It's formed by one metal and one non-metal. And as you can see here, the chlorine can pull off the electron completely to itself, making them more stable as they simulate a noble gas. Now I will explain the electronegative trend. Across the periodic table, the electronegativity goes up, and from down to top, it also increases. That makes francium the least electronegative one, and fluorine the most electronegative one. The values can come from 0 to 4.0. Now I will explain the bond type. There are three bond types. The first one is non-polar. It's from 0 to 0.4 in electronegative. It commonly occurs when two atoms of the same element interact with each other. That's why, because they try to pull out, but they have the same forces. They don't move, and that's why it's called non-polar. The second one is polar covalent. It goes from 0.4 to 1.7, and as I explained before, in this case, the chlorine, that is the most electronegative one, try to pull out the electron from hydrogen. In this case, since it's from 0.4 to 1.7, chlorine doesn't have the ability to pull out completely the electron. That's why they share them. And finally, it's the ionic bond. Since the electronegativity is from 0.7 and more, it has the ability to completely extract the electron from the sodium. That's why you can see like two molecules separated instead of just they sharing them. All of this makes the molecule more stable, like I said before, because they try to simulate a noble gas.
Hello guys, this is Dr. Castro explaining polar versus non-polar molecules. To start with, a polar molecule is going to share the electrons unequally. For example, we have hydrogen and fluorine. Hydrogen is going to be positive, fluorine is going to be negative. So fluorine is going to pull the electrons toward itself, making this molecule share the electrons unequally. Secondly, we have non-polar molecules. So polar molecules share the electrons equally. For example, hydrogen gas. We have hydrogen positive and we have hydrogen positive. They share the same properties and they're both positive, making this molecule neutral, meaning that they are not going to share they are going to share the electrons equally. Secondly, we have molecules made up of the same elements that are going to be nonpolar. So we have here the diatomical elements. So remember this, have no fear of ice cold beer. So as you can see, we have hydrogen, nitrogen, fluoride, oxygen, iodide, chloride, and bromine. So have no fear of ice cold beer. Since they are both of the same element, they are going to be neutral, meaning that they are going to be nonpolar. So thirdly, when we have carbon and hydrogen together, the molecule is going to be nonpolar. Why? We have an example here. For example, methane, we have the hydrogen, which is going to be 2.1, and carbon, which is going to be 2.5. The electronegativity of this is going to be 0.4 because the bond is going to be nonpolar. This structure is a simple diagram that is going to help you understand the rearrangements of atoms and the balanced electrons in the molecule, playing an important role in geometrical shapes and polarity.
Hi, I'm Dr. Baez, and today I'm going to talk about the molecular geometry and its influence on polarity. First, I'm going to divide the molecular geometry in 3 electron geometry sections. The first section, we're going to have a linear electron geometry. They're going to be for 2 domains, 2 bonded, and 0 non-bonded. They're going to have a linear shape with 180 degrees. For the second one, we're going to have a trigonal planar electron geometry. They're going to be these 2 examples. In the first one, we have 3 domains, 3 bonded, and 0 non-bonded. They're going to have a trigonal planar shape with 120 degrees. And for the second one, we have 3 domains, 2, but we have an exception here. We have only 2 bonded and 1 non-bonded. They're going to have a band shape with 120 degrees. The third section has a tetrahedral electron geometry. For example, in this one, we have 4 domains, and the 4 domains are bonded, and we don't have any non-bonded, so going to be 0. And this example has a tetrahedral shape with an angle of 109.5 degrees. In the second one, we have 4 domains. Only 3 of the domains are bonded, and we have 1 non-bonded that's going to be this one. They have a trigonal pyramidal shape with an angle of 109.5 degrees too. And the third one, we have 4 domains, 1, 2, 3, and 4. Only 2 are bonded and 2 non-bonded. They're going to have a band shape and an angle of 109 degrees, 0.5 degrees. How we already have the knowledge about the molecular geometry, now we're going to see some examples of how molecular geometry is related with the polarity. Here we have 5 different examples. In the first one, we have a nitrogen that has triple bonds with another nitrogen. These things that you can observe these are arrows, that the arrows are vectors. The vectors are always going to point out to the most electronegative element in the molecule. Here, how we have 2 the same elements, they're going to point out that they're going to be cancelled out. In this one, in the second example, we have boron, that is point out to the fluorine, that is the most electronegative element in the molecule. How they are the same bonds, they're going to be cancelled out. With an angle of 120, they're going to be cancelled out, so going to be a non-polar molecule. Here we have the third example, that is ammonia. Ammonia, the hydrogen is pointing out to the nitrogen, that is the most electronegative element in this molecule. Also very important, the nitrogen have 1 lone pair, that the lone pairs have the energy. Also, there are no symmetrical bonds with an angle of 109.5 degrees, so there doesn't going to be cancelled out, so going to be a polar molecule. In this one, it's very similar to the ammonia. Water has the no symmetrical bonds and also has 2 lone pairs with an angle that less than 180 degrees, so going to be also a polar molecule. In this one, we have carbon that is pointing out to the most electronegative element in this molecule that's going to be fluorine. So how they are symmetrical bonds with an angle of 109 degrees, they're going to be a non-polar molecule.
Hi everyone, my name is Dr. Quincoses, and today we're going to go over dipole moments. Dipole moments arise from electronegativity differences, leading to molecular polarity. Symmetrical molecules make the cancel dipole moments, resulting in a non-polar behavior. With this knowledge, it's going to help us understand molecular interactions and predict easily chemical behaviors accurately. Methyl fluoride. Let's take a look at this part of the example of the molecule where we have hydrogen single bonded, each one of them to the carbon. And we know that the vectors are pointing out towards the most electronegative, in this case carbon. But if we compare these two, we know that the electronegative value is 1.5, making it polar. Well, in the other case, from between hydrogen and carbon, we know that it's 0.3, making it non-polar. And if we remember, dipole moments occurs within the same molecules. They are connected, the positive with the negative. For example, if we have another molecule of methyl fluorine, the hydrogens are going to be attracted to the fluorine, which is the negative part of the molecule. And otherwise, the hydrogen with the fluorine, and the fluorine with the hydrogens of the same kind of molecule, which are polar. So, as previously learned, polarity is a fundamental concept with wide ranges of implications in chemistry and beyond, from solubility rules to molecular geometry and dipole moments. Each aspect contributes to our understanding of molecular behaviors and interactions. Join us in our daily quest for knowledge as we continue to explore